Hello and welcome back to the FAANG YouTube channel. Today we are solving one of the most legendary problems on Leetcode, number 42, trapping rainwater. Before we get into the question prompt, if you haven't already done number 11, container with most water, stop this video, go do that one, because this problem hinges a lot on how you solve that problem. And if you don't understand that one, then this one definitely isn't going to make sense because it's a lot more complicated and you really have to switch your brain on to understand the solution. Okay. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. Horrible problem if you were just given that without this visual diagram. Oof, my god. Luckily, they do give us this diagram. So we can see that we have these black bars and we basically assume that it's raining from the top and how much water would get trapped here. Obviously, if we look here in this case, like even though water would keep going, it's not just gonna like trickle down. So we don't have some sort of like trickle down effects. There's no overflows here. So it's not like from here it's gonna overflow and then fill this gap. It's just literally where there's a gap between the two. So let's just kind of get that out of the way because I don't know, maybe your brain thinks it can overflow. It can't. So it's literally just gonna fill in the gaps here. So let's look at an example. So if we see this one, obviously we can see that there's a gap here. So this will get filled. And then this area here is going to get filled. So we have, what is this? 1 square. So this is 4 squares here. And then we have 1 square here. So there's a total of 6. Again, this is one of those problems where if you just look at it, it's really easy to solve. But how in the world are we actually going to code this? So if you've seen container with most water, you remember that we had some logic where we were looking at kind of the left pointer of where we were and the right pointer of where we were, and then basically just calculating kind of the area of the kind of rectangle that gets formed, and that was the amount of water in there, and then, you know, we just maximize that. Unfortunately, now we have obstacles, and it's going to be a bit tricky to do that. And the way that we actually want to do this is we're again going to have left and right pointers. So the left is going to start at 0 or wherever this thing starts. And the right is actually going to start at the end of the array. So this is going to be the len of n minus 1, right? So it's going to start here. What do we want to do? Okay. So when we solved container with most water, again, we had some sort of perimeter, some area that we found, and then we computed the amount of water inside of it. The problem with here is that there's obstacles, so we can't just do that because obviously there's things in the way, so we're not able to just get the area. We have to compute it on the fly and then add everything together, and that will be the final amount of water we want to trap. But again, this is a problem because how do we deal with all these bars? It's complicated. So actually what we're going to do is we're going to move our pointers from towards each other. So the left is going to go this way and the right is going to go this way. And obviously when they intersect, then we're done with the problem. And the logic really comes down to kind of solving it in the middle. So what we do at each stage is we look at the current value of the left and the right. And we're also going to track what the left maximum is and the right maximum is, and you'll see why we do this in a second. So what we do is we're going to check, okay, so what is the current value of left? Left equals 0 and right equals 1, right? Can we trap any water here? No, because obviously this has no boundary on the left. Obviously, they haven't told us that kind of the axis here can serve as a boundary, so there's nothing bounding us here. So we cannot trap anything. And remember that we don't know what's going to come in the middle here. And obviously, we're not going to just do it. We're not going to look in here because that would give us a big O of n squared solution if we were just checking what's in the middle for every single one. But you could solve it that way, but that's not the optimal solution. We want to just do this in one pass. So we can't just do that. So we know that there's nothing here, so we can't trap anything at this point in time. So what we do now is we actually want to move the left here. We want to move it to 1. So now left becomes 1 and right is still 1. So now what we see is that let's assume that nothing was in between, right? So we had our axis and we had something here and we had something here, right? That means that we can potentially trap something, right? If there's a gap anywhere, then we can fill it because we know that there will be a bound at the left side and there will be a bound at the right side. So we can for sure trap some water here, assuming that not everything in between is already an obstacle. So if there are any gaps, then we know for sure because the left bounds it and the right bounds it. So there's at least a height of 1 that we could trap. Again, assuming if there's gaps, right? If everything was just an obstacle in between, then we couldn't trap anything. But basically, now that we know that we can at least trap 1 square of water when we see a free one, we can trap it. So this is the basis of our problem, right? We now know that we have bounds which can hold water. And what we want to do is just next a position that we see that we can actually trap something in, we will. So here we can't trap anything because these are both obstacles, right? But if we were to move our left 1 more and left is now 0, because the left max is 1 and the right max is 1, we know that regardless of what is in this bit here, this is free. This has a bound which can hold the water, and the right side has a bound that can hold the water. So we know for sure at this point, we can at least trap this water. We don't know whether this one is going to be high or not. We don't know if it's low. We don't really care. All we know at this point is that this tile here at this stage can be trapped with water. And this is the basis of our solution. We're basically just doing this greedily and adding them up as we go along. So hopefully that makes sense, right? Because we have a boundary on the left side and we have a boundary on the right side. We don't care what's in the middle here because we know that this bit will always be able to hold water. Okay, so now we, add 1 to our solution. So let's just say res equals 1 because we're able to trap, right? So now we can move our left 1 up again, and we're going to move the left here. And now we see that left equals 2. And again, we can't trap any water because this one is actually a boundary. So we can update our left max. So now, because the left max increased, we actually want to move the right side to see if we can find a higher right one. Because say we then found another bit of water, we want to basically trap as much as we can. So because our left is actually 2 at this point, if we didn't move the right pointer up, we could be missing, as we actually will in this example, a higher right one, which could help us trap water. So if obviously we have 2, then that gives us a lot more squares to trap, right? Instead of just, if we have 1, we can only trap, at a height of 1, but if we have 2, then we can trap higher. So because our left is actually higher than the right, we'll actually move the right one to the left to try to find a better right one. So hopefully this isn't gonna get too messy. Let's see, actually, maybe I can clean this up. Let's see. Oh boy. Okay. How do I get rid of all this text? 1 second, bear with me. Okay, that did not do what I wanted it to do. All right, that's okay. Let's just not do that then. Okay. We have this extra space down here. So we know that the left max right now is 2. And now we've moved our right pointer to this one, and we've seen that the right max is also going to be 2. And obviously our result is still going to be 1. Okay, so now we've moved our right here, and our left is still pointing here. So now we can move our left again, and we see that we have a gap, right? But again, like we did before, right? If we draw our diagram, we have 2 here and 2 here. We know that we don't care what happens between the next value. We know that we're here, right? We don't care what happens to the left because we know for sure that we can trap between the left and the right. So we don't need to worry about it. We can just take whatever the difference between the maximum height is of these two and whatever our current one is. So obviously this one is 1. So we can only trap 1 piece of water because there's an obstacle up here. So we can trap this piece and then add it to our result, and then we can move forward. So we can move forward now. So now we've trapped the water here. And then we see that we have another gap here, right? And this one is a gap of 2. So again, we don't care what happens to the right of our gap up until the point where we hit our right. We don't know anything about that yet. all we know for sure is that at this point in time, we can trap these two waters at our current position here with our left pointer, because we know that we're bounded by the left and we're bounded by the right. So we can basically trap all of this water and add it to our result. And essentially what we do is we're just going to repeat this process on and on and on until we basically cross the left and the right, at which point there's no point of keeping going because we've already processed everything. And that's really just the basis of the algorithm. I think what I'm really trying to hammer home is the fact that, let's kind of just get rid of all this text. Bear with me for like 2 seconds here while I clear all this. Okay, that's as far as it wants to go. Oh, Jesus. Okay. Oh, man, I can't. Okay, there we go. All right, I'm not going to touch it anymore. Okay, never mind. What the thing that I want you to understand is that if we have 2 points and we know that, you know, there are obstacles, it does not matter what's in between. When we process something and we see that we can take water, because it is bounded on the left and the right, it can't just like overflow or spill out. We know that we can at least take that one. In that way, we're solving it in a bit of a greedy manner. And we're just taking them as they come. We're just feeling where we are as it comes. So here, if we don't care what comes to the right of this point up until this right boundary, if at this point in time we see that we can fill water, it would fill, right? Assuming that there was nothing else here, then we could just fill everything. So depending on how high the current obstacle is, then that will be how much water we can take. We can either take 2 squares, 1 and 2, or if here is an obstacle, then we can only just take 1. But we know for sure that we can take water here. Understanding this part is really the crux of the algorithm and why I've basically said the same thing for the last 5 minutes, because if you don't understand this part, then you're just not going to get the solution. And this is what really needs to click in your head, that if you have a left boundary and a right boundary, then you can take something greedily because you know for sure that it will be trapped here. It doesn't matter what is to the right of our current position. At this point in time, we know for sure that at least this one can be filled, right? The rest can be boundaries, they can be unusable, but this position will for sure be able to be filled. So this is all you need to understand for this problem. If you don't get this, go back, rewatch it, try to draw it out yourself and figure it out, or let's see the code first and then do it, walk through it line by line, and you'll see what I mean. Okay, let's go to the code editor and type this up. I feel like I've been blabbing for 10 minutes. Okay. We saw the basic intuition, and now let's code it up. Luckily, the code is actually maybe 15 lines. It's really simple. The explanation is the hard part. So let us type this up. Remember that we need a left pointer, a right pointer, and also a variable to store a result. So the left and the right, the left will be 0, and also the result will be 0. So we'll say left equals trapped equals 0, and then the right will be the length of our height array -1, because we start at the very last index. And remember, we're also tracking the left maximum that we've seen and the right maximum we've seen to basically determine how high we can trap, right? Actually, in our case, we only looked at examples where left max and right max were equal, but in the case that they're not equal, then we can only trap up to whichever one is smaller here, right? We can't just overflow just because one boundary is higher. Similar to how we had in container with most water, the amount we can trap is based on whatever the smaller of the bounds is, obviously, because then you'd have water flowing out if you tried to do it the other way. So it has to be whatever the minimum of the 2 maxes here. Okay, so we're going to have the left maximum is going to equal the right maximum, and this is going to equal to 0. And now, like I said, we're going to move the left pointer to the right and the right pointer to the left, and when they cross, that is when we're done. So we're going to say while left is less than right, we're going to say that the current left position is going to equal to heights of L, and the current right position is going to equal to the heights of R. Okay, now what we need to do is actually update our left and right maximum, because our current position may actually be an obstacle, and it may actually be the new highest point that we can use to trap in the future, right? If our current value is an obstacle, then chances are we're probably not going to be able to trap unless it's actually less than whatever the maximum is, but we still need to update it, right? So we're going to say the left max equals to the maximum of the current max and whatever the current left is. And then the right max is the same. It's going to be the maximum, whatever the right max is, or the current right position. Now what we need to do is we need to basically either move the left or the right up and also add to our solution if we have one. Remember, if the left maximum is actually greater than the right, then we want to be moving the right maximum, the right pointer to the left so that we can potentially find a greater right value to trap with. And vice versa, if right is actually greater than left, we want to move it to the right to see if we can find something bigger to trap with, because we don't want to have the case where we never move our left pointer up, and then maybe we have a height of like 5 later on, and then our right pointer's at a 5, and we're actually just trapping with 1 and 5. That's not the maximum, because you can only trap up to 1 here, because like we just said, you can't have an overflow. But if we found the 5, then you could trap at a much higher number. So we're going to say if the left maximum is actually less than the right maximum, then we're going to add to our trapped what? We're going to say the left maximum minus the current left position. So this is the case where our left maximum is smaller, so that determines how much we can trap. So if we kind of look back to our example, when we were, I guess this is, what's a good example here? Oh, because they all kind of equal, but basically it's the case here where we just do the left maximum minus the current one. So the current left in this case, in this block, would be 1. So we basically just do whatever the left max is, which is 2, minus 1 to basically account for the fact that our current position is 1. We can only trap 1 water here. And in this case, we move our left pointer up. Otherwise, in the other case, we do the opposite. So we're going to say trapped is going to be equal to right max minus the current right position, because we need to account for the fact that our current right position may actually be an obstacle as well. You can trap on top of obstacles, as you can see here. There is a trapping between this one and this one. And then we need to move the right pointer down. And then at the end, we need to just return trapped. So yeah, a good example here is, okay, so say our left pointer is here at this big one. This is 3. And then our right pointer is here at this 2, right? The reason we can't trap anything above here is because obviously 2 is not high enough. So we couldn't trap anything up here. It would just like spill over. So we can only trap in this thing because it's bounded by this height here and this height here. So why, even if this one was higher, we couldn't just trap all this stuff, because you need to have the same height at least to trap that one. So that's why we go off of whatever the lesser one is, because that will actually determine how much we can get. Otherwise, it would just spill over. Okay, so that should be that. Let's run this. Heights. Oh, is it called height now? Okay. Heights. Okay, let's just run that again. And okay, looks good. Let's submit this. And accepted. Perfect. All right. What is the time and space complexity of our algorithm? So as you can see, all we do is actually iterate through our height 1 time. We just go from left to right, and we will visit every index at most once. So that means that our solution here is big O of n, where n is the length of heights. For the space complexity, as you can see, this is the most optimal solution, because we don't use any extra space. We just have these kind of pointer variables for our left and right pointer, and the solution, we don't create any extra space, so it's big O of 1. And this is the most optimal solution you can get. You can't do any better than this. This is kind of the gold standard. So yeah, that is trapping rainwater. One where it's really, really easy to code, but actually explaining it is the tricky part. Again, this is a greedy solution, so we're only able to take waters as they come based on kind of where we were able to bound ourselves, right? So, if we have a bound of 2 and a bound of 2, then it really, like in this case, we have a bound here and we have a bound here. It doesn't matter what comes in between, because we know that when we're at this point, we'll at least be able to trap it. We don't care if the rest is actually a obstacle. there's a gap here. We can hold it because we have a left side and we have a right side. So we can just trap, and then we do this in a greedy manner, and that's the way that we're actually able to do it in one pass. Okay, so that's enough blabbing. Hopefully this video makes sense. This one is one that really just takes a while for you to wrap your head around it. If you didn't get this one, then I would just recommend, you have the code here, you know that it works, obviously it was accepted. Literally just go through this example or go through the next example line by line, update what left is, what right is, what the left max, the right max is, go through this logic and, you know, see for yourself how the variables change and why you can trap at each one, and see that you get to the final solution. That's really your kind of last bet for figuring these questions out, is just get a pen and paper, do it the old-fashioned way, and write it out. So hopefully that helps. Hopefully my explanation kind of hammered home the main points here, which is kind of this left max and right max, which decides everything here. Anyway, this video is probably 20 minutes long at this point. If you enjoyed it, leave a like and a comment, subscribe to the channel to help me grow, and have a good one. See ya.